Hello once again. Let's have another discussion on differential equations. But this time, let's talk about variable separable differential equations. From the word itself, variable separable. This means that every single variable in the differential equation can be separated in order for them to basically be integrated right away. So, with that being said, the differential equation can be written in the form of a function of x times the differential x plus a function of y times differential y equal to 0. Okay, so notice from the equation, all of these terms here, the expression here, all of the terms are in terms of x, and all of the terms in this term is in terms of y. So all of the functions with y only is multiplied by dy, and that of x is multiplied by the differential x. So how do we know if a differential equation is a variable separable differential equation? We'll be using algebraic manipulations from the differential equation itself. And once that you can write that equation terms of this form, in this form, then you can say that it's a variable separable differential equation. Now, once that you've rewritten the equation in terms of this form, you can now simply integrate all the terms here for you to determine the general solution. So the general solution here is the integral of f of x plus the integral of g of y, oops, dy, and this is a constant c. So in some books, they write the integral of f of x as the capital F, and this is the capital Y, g equal to c. So some function of x plus some function of y equal to the arbitrary constant. All right. So with this, actually, this is the only part wherein you will apply the concepts of differential equations. Um, all other parts of the solution are plainly a review of your integrals, integral calculus, and algebra. So with the first sample, let's try to solve this differential equation, right? So from this differential equation, as you may notice, this is not yet in the form that we want, but we can manipulate. We can rewrite the equation. We first try to cross multiply. Let's cross multiply the two sides. So this becomes y dy equal to x squared plus 1 dx. Well, actually, we can already solve this since we have already separated the variables. But what we can do is to transpose this to the right side, which becomes 0 equal to x squared plus 1 dx minus y dy. Then try to flip the equation so that everything is equal to 0. So actually, we just have to copy this, then equal to 0. Okay, and with that, we already have the form of the differential equation that we want. Okay, so this is f of x dx minus g of y dy. Okay, that's equal to 0. So now we can integrate all the terms. So by using the power rule, this is 1/3 x cubed plus x, and this is minus 1/2 y squared. And of course, the integral of 0 is the arbitrary constant. Okay, now if you don't want to see any denominator, then you can actually multiply all of these by 6, which is the least common denominator of the equation. So distributing 6, it becomes 2x cubed plus 6x minus 3y squared equal to 6 times c. Okay, here we can write it as is. But in some references, this is what they they will tell you when you multiply an arbitrary constant by a defined constant, okay, it's still an arbitrary constant. So, with that being said, we can actually just simply express the solution as 2x cubed plus 6x minus 3y squared equal to the arbitrary constant. Okay, and that is our general solution. Now, for the next example, of course, the variables are not yet separated. So let's try to separate the variables. Let's cross multiply. This becomes x dy equal to y squared plus 1 dx. Oh, but as you may notice, it's not yet separated. Okay, so how do we place y squared plus 1 to dy and pair x to dx? Let's divide. Divide both sides by x times y squared plus 1. This results to dy over y squared plus 1 equal to dx over x. Or if you want, from the equation itself, you just have to swap these two terms. You just have to swap y squared plus 1 and dx. Swap places, right? Then you can actually separate them. Now, let's try to transpose some variables again. Transpose to the left side, 0 equal to dx over x minus dy over y squared plus 1. And of course, flip, because we want that the equation is equated to 0. The 0 is on the right-hand side. Now we can integrate. So integrating this becomes the natural log of the absolute value of x. That's the formula, right? And then equal to, that's minus the tangent inverse of y equal to the arbitrary constant. Now, in some books, they just want this answer. Some books, this is okay. In some books, they still try to solve for y, okay? So, what can be another form of this general solution? So, of course, let's try to solve for y by isolating x. Okay, let's flip these two numbers. We have ln of x, okay, minus c equal to tangent inverse of y. But as I have said earlier, this is still an arbitrary constant. So that minus c term can still be rewritten as plus c. Okay? And then you take the tangent of both sides of the equation, which results to, of course, tangent of tangent inverse is y. It's equal to the tangent of the quantity ln of x. Instead of writing minus c, we'll write plus c. Okay? So this is another possible form of the general solution. Next up, let's try this example. Okay. Okay, so again, it's not yet separated. It looks like it cannot be separated. But as you may notice, all we have to do is to divide both sides by y times 1 plus x squared. Why? We want 1 plus x squared to be with dx, and we want y to be with dy. So this results to 2x dx over 1 plus x squared plus dy over y equal to 0. Then, again, we can integrate all the terms. From substitution or integration by substitution, okay? Okay, I won't dig deeper into the integration by substitution, but you just have to let u equal to 1 plus x squared here. You deal with the integration on your own. It should result 2 ln of 1 plus x squared. And this is plus ln of y equal to the arbitrary constant. Now, as you may notice from the equation, we have two natural logarithms. And from the loss of logarithms, we can actually use ln a plus ln b equal to ln of ab. So the two va- uh, so the two expressions inside the natural logarithm will, okay, so this becomes y ln of y times 1 plus x squared equal to c. Now, to eliminate the natural logarithm, we just have to raise both sides using the base e raised to the expression. So raising this, the natural log will cancel, and this results to y times 1 plus x squared equal to e raised to c. But then again, e raised to c is an arbitrary constant. So this becomes y times 1 plus x squared equal to the arbitrary constant. Let's have another one. We have a differential equation which really looks like it cannot be separated. Okay, the variables cannot be separated, but with the um loss of exponents, it is possible. Let's rewrite e raised to x minus y by e raised to x times e raised to negative y. And with that, we can separate the variables. Multiply both sides by e raised to y and dx so that we can immediately see the result. That's e raised to y dy equal to e raised to x dx. Okay? Again, by transposing and flipping up the equation, we have e raised to x dx minus e raised to y dy equal to 0. So by integrating all the terms, this becomes e raised to x minus e raised to y equal to c. So actually, this looks simple enough. This looks simple enough, so we don't have to solve for y. This can be our general solution already. Try these examples. And here are the answers for the practice problems. So once again, thank you for listening to this lecture, and I hope to see you in the next one. Bye.